Welcome back everyone to Math 107. We are now, believe it or not, at Lecture 15A. And yesterday, when we were looking at one of the problems on page 456, actually it was number 22 in the book, 21 is very similar to it. It threw me. I had not seen one exactly like that before, so if it threw me, it probably threw you too. So we're going to look at that. We are going to learn to solve logarithmic and exponential equations. We have been preparing for that with our properties of logarithms and our properties of exponents. And the one thing that I've tried to stress over and over is that exponential functions and log functions are inverses of each other. So whenever you're having to solve an exponential equation, most likely you're going to have to take the log of both sides. And whenever you're solving logarithmic equations, you're probably going to have to convert to exponential form to solve. They just work so nicely with each other. And then we're going to move into 4.7, which I call fun with money. Everybody should be interested in money, and this will be in theory, so we can deposit whatever size amount of money we want to an account and earn whatever interest we want. And this is going to lead into interest being compounded continuously. There aren't any banks that I'm aware of that offer compounded continuously, but compounded continuously is very similar to compounded daily, and it's a quick and easy way to approximate how much money is going to be in your account when you have a compounded daily interest. And then hopefully we get into 4.8, our applications, exponential growth and decay. We have like cells growing or a population growing or bacteria growing, exponential growth. And we're going to look at uninhibited growth. That means that it's going to grow forever and ever and ever and ever. But as you know, most things don't grow forever and ever and ever. For example, if you put some fish in a pond, the fish will start multiplying, but your pond really can only handle so many fish before the oxygen in the food supply starts to make them die out. Now those are called logistic growth kind of curves because they'll grow till they get to a certain point and the pond can't handle anymore. Same thing in a city. People will be on top of each other, standing on each other's shoulders if it grew like this forever. But we're not going to look at the logistic the logistic growth, which is a leveling off. We're just going to pretend that over the scheme of time we're talking about, it's going to grow forever and ever and ever. And then we're going to talk about exponential decay. Examples of exponential decay generally are your radioactive substances. That's what we normally think of. There's another application in there that we're not going to look at. It's called Newton's law of cooling. You may have talked about that in your physics books. What happens is you start out with something and maybe a temperature and it comes down. For example, one of the ways that they can tell how long somebody's been dead, that's morbid, isn't it, is they take their temperature, and whatever their temperature is, they can back up and find out how long ago it was that it was at a normal temperature. Or another, there may be a problem actually in your book about that. And another example of the decay kind of deal, as opposed to growth, would be like maybe we have hot coffee in the room, and the room is, I'd say it's about 78 degrees. And so whatever your temperature of your coffee is, it's going to drop in temperature until it approaches the temperature of the room. That represents a decay type problem. So those are some applications. Exponential growth could also be, it's used in medicine for like when they measure maybe the size of a tumor and they're seeing how it's growing over time. They can get its growth rate and predict how big the thing's going to get. There's all kinds of applications, more than I'm sure that's just in your book on these growth and decays. These are wonderful applications to the exponential functions. Okay, then for Lecture 16, be ready for the cumulative review. Work that out in great detail so we can go over it. You will need to omit 10C and 15. 2 problems on there to omit, and then we'll go over that. And then we are going to be ready to move into trigonometry. We'll be there. Okay? Any questions? Are we good? Ready to go? All right, so the first thing I wanted to do was revisit page 456. And I brought in, or borrowed, the Student Solutions Manual on this one because it actually threw me there for a moment. Actually, for a while it threw me. Number 21, yesterday, e to the log of e squared is 16. That was an interesting little problem. Don't know that I had ever seen one before, written exactly like that. We know that if we have a raised to the log to the base a of anything, because exponential and log functions to the same bases or inverses, you get an m. Part that threw me yesterday was there was a e squared on that base. So I tried to figure out, somebody must have just had fun coming up with this. I don't know that I've ever seen it. So I borrowed the solutions manual. I'm just going to show you what they did, which makes absolute sense, but I personally didn't think of it. They're coming in and saying, let's make the exponent here, the exponent, the letter A. So they're just going to make a little substitution for A. Okay? And then going from, it's just, they could have let it be anything they wanted to. They just called it an A. And they went from logarithmic form to exponential form. So that's a e squared to the a equals 16. Then using that power of a power, that's how you get an e to the 2a equals 16. This is in your solutions manual that you got with the book. All right, so then what they wanted to do was really lead you to, I'd like to take the square root of both sides. So they rewrote 16 as 4 squared, just in case you didn't know the square root of 16 was going to be 4. Raising to the 1/2 power means they're taking the square root of both sides. And they came up with e to the a is 4, because 2a times a half. So e to the a is 4. And from here they converted back to log form. So then they say, okay, so e raised to the log of e squared 16, they had called a log e squared 16, but they solved for a again, so the log to the 4, natural log of 4 is the same thing as log e squared 16. I don't know where they came up with this problem, but this is interesting. So since they solved that those were the same thing, they changed that to a natural log 4. Now you can just use your identity, e to the log to the base e of 4 is 4. Quite interesting, and I call things like this, for myself, interesting learning experiences. That was a good problem. I don't know where these guys came up with it. They didn't have one in the exercises, and in fact, I probably will just write them and say, you know, a little hint here would have been nice on these problems. Okay? All right. Of course, I'm not doing this to you on a test through me, but I think it's always interesting to see how to work something. Okay? Everybody good? They just said, let's make a substitution. That's the way math people are. When they can't do something, they just go, well, let's just call it something. Let's call it an A and do it. All right. I just showed you from the Student Solutions Manual. All right. Interesting, interesting. Okay. We're ready to go with section 4.6 in the book. Section 4.6. And we're going to solve some log equations using the properties of logarithms. Properties of logarithms, and those properties came from section 4.5. Let's just look at them real fast. Back on page 449. Log to the base a of 1. Log to any base a of 1 is 0. You'll remember that when you graph y equals log to the base a of x, your curve looks like this. Basically looks like any base. So it goes through the point 1, 0. So therefore log to the base a of 1, when x is 1, the y value is going to be 0 if you want a visual of that. Or if you wanted to convert it to exponential form, you see that log a to the 0 is 1. So that makes sense. And of course, log to the base a of a is 1 because you could put a little 1 exponent up there and you see that that is equal to 1. Okay, 1 and 2 at the bottom of page 449, those are your identities. It has to be a to the log base a of something. Now, let me point out again to you, just so you're careful on this. If there were a 3 maybe right in front of that log part, like a to the 3 log base a of m, that is not fitting that identity. That has to be a 1 right in front of log base a of m. It's got to fit the rule exactly before you can say it's equal to m. With that in mind, suppose your problem was 3 raised to the 5 log base 3 of 7, for example. Do you see how this is not fitting this rule exactly? This only has a 1 in front of the log. Do you see? Okay, so what can you do to make it fit the rule? Yes?
Couldn't you make it like log base 3 to 7 to the 5th?
Absolutely. He's using his property of logarithms that says this number out front, which is the property on the other next page, property number 5, log to the base a of m to the r is r log base a of m. So he's using that property, suggested that I use that property there. So let me get back over here. So this is equal to 3 log to the base 3 of 7 raised to the 5th. Now if you look at this, we have a, which is 3, 1 log base 3, and the 7 to the 5th represents my m. So according to this identity, that is just equal to 7 to the 5th, whatever that is. Does everybody see how it has to fit the rule exactly? Okay, same deal with number 2 on this page. Let me just flip it over. Log to the base a of a to the r is r. But suppose you had something like 6 log to the base 2 of 2 raised to the 10th. Okay, that is not fitting the rule exactly because there's really a 1 right in front of that log to the base a of a to the r. So we just looked at that property. We could rewrite this log to the base 2 of 2, sorry, that 2 didn't, let's write it right here. This equals log to the base 2 of 2 to the 10th, and then what are you going to do with this 6? That's going to be the exponent on this argument, and then power of a power, exactly right. It's log to the base 2 of 2 to the 60th power. You multiply those exponents. Now we're fitting the rule exactly. It's 1 log to the base a of a to the r, so this is equal to 60. Do you see, everyone? Do you see? It's like a game. It has to fit the rule. You can't get creative and make it work like you want it to. You have to make it work like the rule. Okay. And then, of course, yesterday we talked about those properties that when you have the log of a product, anybody remember why you added these two terms? What was the relationship here? We did a proof on this yesterday. Why do you know you're going to add when you multiply? Right, it was like when you converted to exponential form, and when you multiply with like bases, you add the exponents. And this value right here is the value of the exponent. Okay, and the reason you subtracted when you had division was because when you divide with like bases, you subtract the exponents. And then the last one, which we just did an example of, the reason there's a multiplication there is because it goes with the power of the power rule for properties of exponents where you multiply. Okay, so back on 453, we're going to use these today to help us solve some log equations where we might need to take the log of both sides of an equation. or when you might say the arguments are equal when you already have a log equation with logs on both sides. Okay, so we're going to solve some log equations and some exponential equations, and we're going to use our properties of logs. So I'm going to start out with a couple simple examples, and then we'll jump on some examples from the book that are a little more interesting. So let's start out solving log equations. Okay, so really we are solving for the variable. It's an equation. We have an unknown x. Let's start out kind of easy. 2, here's my example, 2 times the log to the base 3 of x equals 10. 2 times the log to the base 3 of x equals 10. Okay, I'm going to tell you what I want to do, and then I need you to tell me, can I do it or not? Okay? So what I want to do is I want to go 3 to the 10th equals 2x. Can I do that? Why not?
You just have to do something with the 2.
You are so perfect. This 2 right here is a little problem. You can't convert to exponential form until this 2 is equal to what? What has this got to be equal to right here? 1. This must be a 1. So this is 2 times log to the base 3 of x is 10. So what do you need to do to get that to be a 1? Multiply through by half or divide by 2. So you have log to the base 3 of x is equal to 5. We multiplied both sides of the equation by half. Multiply by half or divide by 2, same thing. Okay, now there's 2 ways to solve this problem from here. So we're going to do both ways, and then you can do whichever way you want to. Give me one way. Okay, flip it to exponential form, and you get x is equal to 3 to the 5th. And you can plug and chug away on your calculator if you want to know what that's equal to. Okay? All right, somebody else tell me another way you can solve this. I gave you a word yesterday that's not in the precise encyclopedia of mathematical vocabulary.
Exponentiate.
You're right. Exponentiate both sides. That means let's let both sides be the exponent for some base, and then use an identity. So if this is log to the base 3, what base do I need for both sides of my equation? 3, y'all are very good. So we can say 3 raised to the log to the base 3 of x is equal to 3 raised to the 5th. We can let both sides of an equation become the exponents for a base, and we get to pick our base. We pick this base 3 because we have an identity that says a raised to the log a of x is x. So 3 raised to the log 3 of x is x, and we got x equals 3 to the 5th. So 2 ways you could solve that. All right, everybody good? Okay, let's try another example. What about natural log of x plus 3 equals 7? Okay, let's do it 2 ways. All right, we're solving for x, and I want to hear you verbalize what kind of equation this is so you'll hear your brain when you're on a test. What kind of equation is this? A natural log equation, because you see logs in it. Okay? So your brain's going to go, whenever the argument has a variable there, I probably got to get to exponent form. All right, so 2 ways. What would be one way?
Put it in exponential form.
Okay, what's the understood base here?
E.
So to switch it to exponential form, it's going to be x plus 3 equals e to the 7th. So x is equal to e to the 7th minus 3. By the way, this is an exact answer, because e to the 7th, when you put it in your calculator, is just going to be an approximate answer. A lot of times on your test, it will say leave answers exact. and that's all we're asking for. Anybody can go plug and chug e to the 7th in your calculator and subtract 3 to get an approximation. Okay? All right. If you want to exponentiate both sides, what's my base going to need to be? E. Let the base be e, and we have natural log x plus 3 equals e to the 7th. Let both sides become the exponent for e. I use my identity, a to the log to the base a, because they have the same base, is equal to this part. So x plus 3 equals e to the 7th. X is equal to e to the 7th minus 3. Check. Okay, everybody good? All right, so that just illustrated a couple of your identities. I'm going to pull 2 problems out of the exercises, and then we'll go to exponential form. All right, these are coming from page 461. The first example I want to do is number 14, and maybe, just maybe, it's a WebAssign question to help you out. Log to the base 4 of x plus log to the base 4 of x minus 3 equals 1. And our instructions are to solve for x. Okay? All right. My job is to solve for x, but I have a logarithmic equation. You see the log there. But I have 2 terms. And I need to find a way to get this to a single log expression to be able to solve. What are you going to do, everybody? That's exactly right. You have your properties that when you have log to the base a of m plus log to the base a of n, property number 1 of laws of logarithms, this is equal to log to the base 4 of what? Times x minus 3. Okay? All right, so we have log to the base 4, and I'm going to multiply that out. It gives me x squared minus 3x equals 1. Okay, everybody know where this property is coming from? Do I need to flash it back on the screen? Yes, no? Okay. All right, so now we've got this to a single log, and my job is to solve for the x. Tell me, everybody, what we're going to do. Going to go to exponential form. Maybe you just want to convert it, so we'll go x squared minus 3x equals 4 to the first. What kind of equation do we have here? What's that equation called? Quadratic. How do we solve a quadratic equation? Okay, we've got to get 0 on one side first, right? So we got x squared minus 3x minus 4 equals 0. And this factors mean write as a product. X minus 4, x plus 1. 2 factors multiplied together, so x is 4, x is negative 1. Okay, let's back up a second. Let's back up a second. I'm going to put, I wish I had a red pen. I'm going to put a big alert on here. Alert. Write this in red in your notes. We have an alert here. Let's go back up here and recall domains. What must be true of x in order for you to be able to find the log to the base 4 of x? What must be true about this x, this argument? Recall, x has to be greater than 0. X has to be greater than 0. What did we just find down here as one of our solutions? Negative 1. All right. The alert is when you are solving log equations, you must check for what are called extraneous solutions. Extraneous solutions means because we applied some properties, we may have introduced a solution that really isn't there by using this property. Just like when you square both sides of an equation, you may be introducing an answer that really doesn't work in the original problem. So by applying the properties of logarithms, you may be introducing an answer from the algebra part that really does not work in the original equation. So what always happens, I'm always scared to use always. I'm not aware of any case that doesn't work this way. When you look back, you just want to make sure that you're not going to be trying to take the log of a negative number. So x equal -1 is an extraneous solution because you can't take the log of a negative number. If I put -1 in here, that really messes it up. 4, I can take log to the base 4 of 4. What's that equal to, everybody, quickly? 1. And then log to the base 4 of 1. What's the log to any base of 1? 0. So 1 plus 0 is 1. So it checks. Okay? All right, so what's the alert? The alert is once you apply some properties of logarithms, you may be introducing some fake roots, and double check. And the double check really is going to come from trying to take the log of a negative number. Everybody good on that? Okay, that was number 14, and I had another one I wanted to do. The other one I wanted to do was, where is the one I wanted to do? Okay, we'll jump down and do like number 36. This is also a log equation. Number 36. Oh, those have got A's. I didn't want to do one with A's. That's okay, I'll still do A's. Log to the base A, it's just telling you any base A of x plus log to the base A of x minus 2 equals log to the base A of x plus 4. All right, what do you notice that's different already about this equation than the one that we just looked at, number 14? Make a comparison. What do you notice right away, the difference between 36 and our rhythm? On the right-hand side of the equal sign, before there was just a number. Now we have a log to the base A of x plus 4. All right, so I wanted to point that out because some people don't seem to notice that. This one, when it had a number, I got this to a single log and converted it to exponential form. All right, now we're just going to apply the property from the previous section on page 453 that says when you have the log to the base A of m equal log to the base A of n, the arguments have to be equal. See, they have a log on both sides of the equation. Everybody see that? Okay. So, I would like to apply that property. What do I need to do on the right first? Left. This is left. What do I need to do on the left first? Okay, get it to a single log expression. So it's going to be log to the base A of x times x minus 2. And this equals log to the base A of x plus 4. Log to the base A, x squared minus 2x equals log to the base A, x plus 4. All right, so log to the base A of this argument is exactly equal to log to the base A of this argument. So if they have the same bases, it's clear that the arguments have to be equal, correct? So x squared minus 2x equals x plus 4. Okay, again, we got a quadratic equation. So we need to get a 0 on one side. That almost looks like the same problem we just did, didn't it? Subtract x from both sides, subtract 4. It factors to x minus 4, x plus 1. We have two solutions, x equal 4 and x equal -1. Are we happy to circle that on the test and move on? No, we got to have what happen? A big alert. Alert. You got to check because we could have introduced a fake root here. Do you see one right away that's not going to work? -1, because we can't take the log of a negative number. So x equal -1 is not going to work. Let's just show you what the calculator is going to do when you put in a log of a negative number. Doesn't matter what base. I'll just do log of minus 8. What do you think it's going to do? Hey! Okay, what they do, this particular calculator is putting it in complex notation. There's a little comma in there. All right, so they're trying to give you a complex value for that. This calculator's a little too smart. Most of the time would just tell you it's an error message. Okay, sorry about that. That's a complex solution. In case you can see it, there's a little comma. Do you see the comma between the 2 and the 1? All right. Yeah, I was expecting error. Usually you get error. What'd you say?
Give you that. It gives you an error.
The new calculator gives you an error message?
Yeah.
Okay. Yeah, I was surprised that gave me that, actually. I was trying to see whose calculator I took. All right. Everybody good on this? You're watching the alerts? All right. Let's spend some time now with exponential equations. Those were logs. Now we want to look at exponential equations. All right. Suppose we wanted to solve for x, and you have 2 to the x equals 5. We've looked at these before. Now, I think it was in section like 4.3 in the book before, you would have problems like 2 to the x equals 8. And we were able to get like bases. And when the bases were the same, the exponents were equal. I think you just had that on one of your tests. All right, but here, it's impossible to get like bases. And whenever our argument is up in the exponent and we have an exponential equation, everybody's going to remember to take the log of both sides. Now, we actually can do this problem 2 ways. I think the easiest way is just take the log of both sides. It doesn't matter if it's common log, natural log, or what. You can do whatever you want to. If we take the log, I'm just going to do natural log. Natural log of both sides. Okay, remember we just had a property that says if m equals n, then the log of m is equal to log of n. Take the natural log of both sides. Now how do you get this x out of the exponent? How do you get this x out of here when you got log of 2 to the x? Where can I put the x? In front from that property. I'm going to apply this property, I guess they called it number 5, back on page 450, right here, m to the r. And see, the r in my problem is the exponent, so I'm bringing it up front. Okay, property number 5. All right, so I'll call it property 5. So this is x log 2 equals natural log 5. So x is natural log of 5 over natural log of 2. All right, so all I did was take natural log of both sides. That was one way to do it. That's probably the most popular way to do it. Just if you have an exponential equation, just take the natural log of both sides. Common log, log to any base of both sides. All right, but the other way we can do is just convert to log form. If I were going to convert this to log form, it's going to be log to what base? 2 of 5 equals x. So now my question is, these two answers look very different. Somebody help.
You use the property where you do the 5 over 2.
You are so good. What's that property called?
Something.
Change of base. Change of base. Now, I just want to tell you, this is fine. This answer, x equals log to the base 2 of 5, is perfectly great unless the instructions say you must write it in terms of natural log or you must write it in terms of common log. This is a perfectly great answer. But all I was trying to do was show you that these two things are the same, and wanted to bring you back to the change of base formula, which is on page 453 at the bottom. Page 453, reminding you of your change of base formula. All right, 4.5 had a lot of properties in there. All right, so change of base formula, and if I wanted to go to natural logs, that would be natural log of 5 divided by natural log of 2 equals x. It could also be common log of 5 divided by common log of 2. It could be log to the base 7 of 5 over log to the base 7 of 2. That ratio would always come out to be the same value. All right, everybody good on that? Happy? All right, so there's a exponential equation. Let's go to another one. We're still solving exponential equations. Solve for x. All right, 3 times 2 to the x equals 5. Looks very similar to the last example we just did, except now it's 3 times 2 to the x equals 5. Am I going to want to jump right into taking the log of both sides, or switch into log form? Is there something I need to do here before I start trying to solve this? Is there something getting on everybody's nerves? Thank you. Glad the 3's getting on your nerves. I need a coefficient of 1 in front of my exponential form. So I need to get 2 to the x on a side by itself. So we divided both sides by 3. Now I have 2 to the x equals 5/3. And my choices would be to solve. What's one choice? Just take the natural log of both sides. What's my next step when I do that? Just bring that little x in front, right, using your properties of logarithms. That's x natural log 2 equals natural log 5/3. So x then is natural log 5/3 divided by natural log of 2. And that's an exact value. You could punch away again in your calculator. Yes?
Why did you hit the natural log?
Your property says that anytime, this is back on 453, that anytime you have an equation m equal to n, m, n, and a are positive real numbers, then you can take the log of both sides of an equation. And I always pick natural log because it takes less effort to write it than log. I could do log of any base. Most physical problems go to natural or exponential functions and natural log, and I'm just in the habit of always using natural log. But I could have used anything. Thanks for asking. Everybody good? Okay, what's the other way I could work this problem? Instead of taking the log of both sides, natural log, go to log form, so that would be log to what base? 2 of 5/3 equals x. Explain to me, everybody, use the words. Why are these two things the same? What's the theorem called?
Change of
base.
Good. Change of base formula. Change of base. They're equal. All right, are we good? Okay, one more thing, and then we're going to work a couple problems from the book, and then move on. One of the things that I said in the beginning was that a lot of times we convert to a base e when we have some properties and we're working in physical type problems. And I wanted to just say that any number can be rewritten as e to some power. So if you wanted to know e to what power is 10, that would be because maybe in our problem 10 is a number that we need to convert to an exponential type expression, natural exponential. So if e to the x is 10, what is x, everybody? What is it? How do you solve this for x?
You put it in logarithmic form.
Okay, you could put it in log form or just take the natural log of both sides. What's the natural log
1.
of e to the x? X. And so x is equal to
10.
natural log of 10. So if you were working some type of physical problem and you had something like 10 to the x plus 3, and you needed to convert to base e, you would know how to convert that 10 to a base e, because it would be e to the natural log of 10 raised to the x plus 3 power. So you can get it converted to a base e. All right, I just wanted to point that out. I don't know that your book makes a big deal about that. All right, let's go back to 461 and work a couple exponential problems. 461. Oops, got a mess. Page 461. I think I wanted to look at problem number, oh, this one's easy, 22. Don't know why I picked that now that I look at it. All right, quickly tell me, what do I do? What do you guys like to do? Take the log of both sides or convert it? Natural log of both sides? That's what I would say the majority of people do. Again, what's your next step? Bring the x in front. How do I know I can bring that x in front? By property number 5. That's good, you got that memorized already. So x is natural log of 14 over natural log of 3. Okay, let's see, what other problem do I have? 30, 12, nope, 22, we did that one. 35, we did that one. 39, okay, I guess that's it. All right. I don't see any that are really any harder that you're required to do. We'll try number 26. That one looks pretty hard. 26. 2 to the x plus 1 equals, let's start a new page on that. This is probably the hardest one you would ever have to do for this class. 26. 2 to the x plus 1 equals 5 to the 1 minus 2x. And your job is to solve for x. All right. What would you do here? Same as always. Take the natural log of both sides. All right, let's see what we're going to do. Natural log of 2 raised to the x plus 1 equals natural log of 5 raised to the 1 minus 2x. What's your next step? Same thing that you did for when you were solving the simple one, right? Bring your exponent down front, because your job is to solve for x. You're trying to get it out of the exponent. That's why you're going from exponential to log. Be careful with your parentheses. Okay? Now what do you think you do? What's my job? Solve for x. So I'm going to find a way to get all the x's on one side, all the numbers on the other. What would you suggest that I do?
Would you bring the 1 minus 2x on one side and put natural log of 5 divided by natural log of 2?
Okay, that would be a direction that you could think about doing, and that would be a good thought, because I know that's going to lead to even another mess. I am going to do that on blue. There was nothing wrong with your decision to do that. I just want to show you what you're going to get once you get there. Okay, then what would you have to do?
No, and 2.
What'd you say?
Subtract, wouldn't you? No, that's exponents, never mind.
Did you say natural log of 5 minus 2? Okay, I'm glad I asked you that. Is the natural log of 5 over natural log of 2 equal to natural log 5 minus 2? No. No. Because it's the natural log of m minus natural log of n is natural log of the quantity m divided m minus 2. Okay, so it's not equal to that. Okay, so if we get this far, then what would you do? You're still trying to solve for x, so how are you going to... Looks like you'd have to cross multiply, right? So you'd still, and if you cross multiply, where are you? Right back where you were. Okay, so you know, one's first thought would be exactly what you said. Okay, but then you find out you're just on a merry-go-round. I call that a merry-go-round when you get right back where you were. All right, so that was a thought, nothing wrong, but it didn't work. All right, so what would you do then? I'm trying to get x. I got to get all terms with x together. What are you going to do?
I know how to do it. Move. Put the.
Y'all are all just going to go when we do it.
Yeah.
What would you do, Anna? You don't know what you do?
It's like I can see it, but I can't put it into words.
I can run away and scream.
All right, let's just scream then together. Aren't you just going to multiply out so you can get all your terms separated? All right. So we have x times the natural log of 2 plus natural log of 2 equals natural log of 5 minus 2x natural log of 5. Just like if you had an equation that didn't have a log in it, you know you need to get all the little terms separated. So now you need to get everything with x on one side and all the other numbers on the other. So we have x natural log of 2 plus 2x natural log of 5 equals natural log of 5 minus natural log of 2. Are we starting to feel a little better now? What's my goal? Solve for x. So how do I get an x out of these two terms? The big F word, factor. Factor out the x. Log 2 plus 2 log 5 equals natural log of 5 minus natural log of 2. Are we almost there? X is equal to natural log of 5 minus natural log of 2 over natural log of 2 plus 2 natural log of 5. And you could just punch away on your calculator if you wanted to get a good approximation to what that is. My guess is the back of the book is not going to leave it like that. Is there anything wrong with this? Nope, because you could hurry up and get to the answer. But let's see how you would simplify that so that we're working on our properties of logarithms, okay? All right, is everybody good this far? This is the step that threw you right here, multiplying this out, then getting your x's together. You need to do the big factor word, okay? All right, now let's just simplify this so that we'll see using our properties. Okay, so we have x equals. Now how are you going to deal with log of 5 minus log 2? What's your property where you subtract?
Divide.
Divide. So the numerator is going to be the natural log of 5 divided by 2, which is 2.5, right? 2.5, right? Log of 5 divided by 2, that's 2.5. Okay. Now how are you going to deal with this 2 in front of the log 5 here?
Put it 5 squared.
Okay, so you got natural log of 2 plus natural log of 5 squared, which is 25. All right, so now we have natural log of 2.5, and what's in the denominator? Natural log of
50.
2 times 25, which is 50. And my question is this equal to natural log of 2.5 minus 50?
No.
No. We're done right here. That's probably what you would see in the back of your book. to simplified. This part right here is really fine with these nice little calculators. If you need an approximation, you just find it. But if you were trying to match the back of the book, notice that when you look in the back of the book, if they have it simplified down to one term, that tells you you're probably going to be applying some properties of logarithms to make it match. Is everybody good? Okay, we can solve exponential and log equations. All right, we're going to have to stop here because that was a fast hour, and we're going to look forward to fun with money at the beginning of the next hour. Okay? I don't know. All righty, we are on. So, welcome back to Math 107. We're at Lecture 15B. One of the little things I forgot to do that I really wanted to do was to look for x and y intercepts, approximate them for log functions and for exponential functions. So we're going to back up a second and just do that. Then we're going to do our fun with money, our application of our exponential functions, and then fun with exponential growth and decay type problems. Okay, but first I want to back up a second. We learned how to graph logarithmic functions, and let's just do a quick little review. Y equals log to any base a of x, of course where a is bigger than 1, positive. What does the graph of this look like, everybody? Graph? Yeah, it goes through what point? 1, 0. What's your asymptote?
X equals 0.
X equal to 0 is your asymptote. So for log to the base 5 of x plus 4, it's still going to have the, if it was just log to the base 5 of x, it would still have this look.
Yeah. Alright. This might be a stupid question, but why does it go through 1 through 1, 0?
Okay, the question was, why did it go through 1, 0? If you convert to exponential form, a to the y equals x, if you let y be 0, a to the 0 is 1. That help? You convert it to exponential form. And it's also the inverse of y equals a to the x, which goes through the point 0, 1. Your exponential curve, and this is your inverse, so you interchanged your x and y. Yeah?
Could you set that up like an exponential and still get the same graph, or it has to stay in a log form?
You could set it in exponential form and just put in a bunch of points.
Okay.
But hopefully, I'm hoping that you're going to visualize that if it's log to the base a of x, your graph's going to look like this. And then what does this plus 4 tell you you're going to do? Shift it to the left 4. So that means your asymptote is going to come over here to x equal negative 4. What is going to be your x-intercept now? This 1, 0 has been shifted that way 4, so what's this x-intercept? I'm going to take horizontal, this 1 is going this direction 4, negative 3. The graph's going to go like this, but I wanted us to go algebraically and find some of these x and y intercepts. All right, we know what the graph looks like. Let's do an x and y intercept. Okay, when you were looking for x-intercept, didn't you let y be 0? So for the x-intercept, we let y be 0. 0 equals log to the base 5 of x plus 4. All right, so now we have a log equation. How do we solve this log equation? It's a log equation. How do you solve a log? Go to exponential form. So you have 5 to the 0 equals x plus 4. 5 to the 0 is 1. X equals negative 3. That's what we knew the x-intercept was going to be, and we just solved it algebraically. All right, suppose we want to find the y-intercept at x equals 0. So y is equal to log to the base 5, 0 plus 4. This is log to the base 5 of 4. That's an exact value right here for the y-intercept. But suppose I wanted an approximation. How would I find the approximate number that is? Because that's kind of meaningless to some people, log to the base 5 of 4. Go to your change of base formula. You can say natural log of 4 divided by natural log of 5. We want to find out what that is. Natural log of 4 divided by natural log of 5. That comes out to be approximately 0.86. That's an approximate value. The real value is log base 5 of 4, but this is approximately equal to 0.86. So you have an idea of where it's touching the y-axis. Okay, is everybody good on that? So see, you've been solving exponential and log equations. Here's a good reason to do that, to help you find your x and y intercepts. Okay, now let's go back to the exponential equation. Was that too fast? Did I flip too fast? Are you still writing? Let me back up a second. Hey, I need to read anything? Good? Sorry. Okay. What's the basic graph of y equal e to the x look like? Yeah, it's going to go through 0, 1. All right. So what's going to happen to this graph? Yeah, you're going to go left 3 and what? Down 5, right? So you're going to go left 3. I'm just going to do a little translation of axes in here. And down 5. Okay, and so all you're doing is picking up that graph, moving it left and moving it down. And so what's this point right here going to be? The graph's going to go like this somehow. What's this point right here going to be? -3, what? -4. You're so perfect. Your asymptote is y equal to -5. Remember your asymptote up here is y equal to 0? Asymptote? Okay. But my question is, this curve is going to continue on somehow. It's got to cross the x and the y-axis. So now we've learned how to solve exponential and log equations. Now we can find out approximately what those x and y intercepts are. Okay? All right, so let me solve this. Okay, y equals e to the x plus 3 minus 5. Let's solve for the y-intercept. Y-intercept. Remember, you let x be 0, so y equals e to the 3rd minus 5. That's a perfectly great answer, except that we don't know. We'd like an approximation if we're putting it on our graph. So we'll say e, oops, e. Where is e? E raised to the 3rd minus 5. So that comes out to be approximately 15.09. All right, so somehow my graph was off a little bit. That's going to go way up here. Okay, this is approximately 15.09. Okay, clearly not drawn the scale. All right. And if we want to find the x-intercept, algebraically, we let y be 0. All right, so now we have an exponential equation. I'm solving for the variable up in the exponent. What's going to be my first step solving this, everybody? What's my first step? Are we ready to jump right on the log form, or what else? What do we got to do first? You got to get the base with the exponent on a side by itself. So you're going to add 5 to both sides. Okay, now I have the exponential equation, the base with the exponent. What are you going to do? Take the log of both sides, that's fine. Natural log of 5 is equal to natural log of e to the x plus 3. What's the natural log of e to the x plus 3 equal to, everybody? X plus 3. So x then is negative 3 plus natural log of 5. All right, let's see what that is. Natural log of 5. Did I lose you? We just spent time solving exponential and log equations. And one of the reasons you'd want to do that is to help you be able to find x and y intercepts for your curve sketching.
Is this a section?
This is the section, well, you learned how to graph log functions and exponential functions by shifting around. Now the finale of this whole section, in my opinion, for the reason you learn to solve exponential and log functions is so that you can go back and fine-tune your graphs and be able to identify those x and y intercepts. And you already knew how to find a y-intercept. You let x be 0. That was nothing new. And then you're down to an exponential equation. And the x-intercept, you let y be 0. You just spent section 4.6 learning to solve a problem like this. So it's combining your concepts and putting them together for how you use this kind of thing. All right, so natural log of 5, subtract 3. This comes out to be approximately negative 1.39. And so what happened is, I should have done the graph afterwards. We did a shift, didn't know exactly where it was going through. If this is negative 1, it would have come in somewhere right along here. So the graph should come in and then, oops, and then hit your 15 up there. All right, so you could have gotten a much better graph with x and y intercepts if you'd solved for them as you were doing your shifting around. Okay, especially when you're so far away from the x and y axis. All right, everybody good? Okay, let's play with the money. These are called applications of your exponential functions. Applications of exponential functions. Did I lose my voice? Alrighty, we'll give this a try. That was your moment to be on tape and you didn't do it. Do what? That was your 15 seconds of fame and you missed it. Okay, application of the exponential function. The first one is compound interest. Most financial obligations are based on compound interest. Your home loans, car loans, your money in your savings account. The compound interest is simply simple interest applied over and over. Okay, so first of all, instead of just saying the formula for this dropped out of the sky, by the way, we're in section 4.7, instead of saying the formula for compound interest drops out of the sky, I'm going to do a little, what I call a time diagram. We're going to put $100 in an account, and we're going to let it earn 6% compounded annually, so that we understand what that means. Okay, so I'm going to mark off at the end of 1 year. So what's going to happen is you deposit your $100 at the beginning of the year, and it's going to earn interest. Compound interest is exactly equal to simple interest for one conversion period. So if it's compounded annually, then simple interest for 1 year would be the same thing as compounded annually. All right, let me write that down. Compound interest equals simple interest for one conversion period. Meaning that if it's compounded annually, simple interest for 1 year is the same thing. If it's compounded quarterly, simple interest for a quarter is the same that you'd get for compounded quarterly. All right, the reason we want to say that is because everybody knows the formula for simple interest. Simple interest is equal to PRT, right? PRT, principal times rate times time. Everybody remember that? P stands for your present value, the amount deposited. R stands for the interest rate, and T stands for time expressed in terms of years. So if it's 3 months, how would you write T? 3/12, which is 1/4. If it's months, what's T? 1/12 of a year. If it's days, what is T?
1/365.
What'd you say?
1/365.
1/365, but guess what? There's a little rule that bankers sometimes use because it results in more money for them, and they use time as a day as 1/360. And that gets them a little bit more money if you borrow money from them. It's called banker's rule. Benefits the lender. Okay, but we would use 1/365 here. All right, so if I wanted to, I'm going to call this a little piece of zero representing the initial amount, and we're going to solve for a piece of 1. What I'm doing is developing the compound interest formula that many of you have already memorized. So piece of 1, this amount right here, is going to be what you start out with, 100, plus your interest on 100. That's principal, rate, 6%, and your time is 1 year. So this is equal to 100 plus 6, or 106. Okay? Now if we want to go a second year, piece of 2 is going to be, this is why compound interest is interest on interest. We take our new balance at the beginning, so that's 106 plus your interest on 106 for 1 year. So that probably is about 106 times 0.06. $6.36. And when I add that together, that gives me $112.36. Compound interest means that you're earning interest on top of interest. So see, the first year you only earned $6, but the second year, because you left the money in there, you earned an extra 36 cents because you got interest on top of interest. And what I want to do in developing your formula is go with the symbols. This is P sub 0 for 100. And this gives me, if I factored out a P sub 0, that's P sub 0 times 1 plus 0.06 right here. All right, P sub 2 is P sub 1 plus P sub 1 times 0.06 times 1. And if I factor out a P sub 1, I get P sub 1 times 1 plus 0.06. Now here's the finale of getting to the formula. P sub 1 came from this part right here. So making that substitution, that's a P sub 0 times 1.06 times this 1.06, which is P sub 0 times 1.06 squared. So the balance at the end of the second period is going to be your initial investment times 1.06 squared. If you follow the logic down, what do you think P sub 10 is going to be equal to? The amount at the end of 10 periods.
P0106 to
P
the
sub
10th?
0 times 1.06 raised to the 10th is the 10th conversion period. All right. If you did all of this with symbols, you would come out with a formula that you're going to memorize, if you haven't already memorized it. And that formula is on page 465. And the formula is A equals P times 1 plus R over N to the NT. Remember that formula? This is what I was calling like P sub 10, P sub 3. This is the future value. This is called the present value. Sometimes people call it the principal. Okay. R is it's called nominal rate. Nominal rate. It's called nominal rate, meaning it's the rate you see named in the problem. Is it 8% per year, 8% compounded quarterly? What rate do you see named in the problem? N represents the number of interest conversions in 1 year. So if it's compounded quarterly, N is 4, because interest is tacked on 4 times. If it's monthly, N is 12. All right. Now, I just want to show you that this is that good old simple part of the simple interest. R times 1 over N. R over N is the same thing as R times 1 over N. Okay. N is the number of conversions in 1 year. So when you had simple interest, you had PRT. Here's the R. T is 1 over N. So the question is, how many conversions in 1 year? So if it's compounded quarterly, for our formula here, you're going to be using 4. That meant every 1/4 year. Or if it was monthly, you would have used a 1/12 for your time in terms of years, but they're using an N here to say there are 12 conversions in a year. Do you see how these two formulas are really coming together? All right, so N still is the number of conversions in 1 year, and T is total years. All right, so if we were just working with our problem before, invest $100 at 6% compounded annually for 2 years. All right, because we worked it out longhand. Let's use it in our formula. The P is the 100. The 6% is the R. We got to write it without a percent symbol. Annually is where we're going to get the N. 2 years is where we're getting the T. Okay, so when we put it in the formula, the future value is P, 100, times 1 plus the rate. How do you write 6% as a decimal? 0.06. Annually means how many conversions in a year? 1. And up here we'll have 1 times 2, which is 2. So I have 100 times 1.06 squared. And when we put that in our calculator, remember you square it before you multiply times 100. 1.06 squared times 100, and there's our 112.36 that we just figured out when we applied simple interest after simple interest. Compound interest is just interest on top of interest. Okay? Everybody got it? All right, so let's make up a fun problem. Fun problem. Okay. How much money do you, okay, let's make it up this way. Your rich uncle. Anybody have any of those? Uncles. How about just one? Uncle. Gave you $5,000 the day you were born. Your mom, because moms are smart, invested it at, we'll say, 6% compounded monthly. Okay, so your rich uncle gave you $5,000 the day you were born. Your mom invested it at 6% compounded monthly. Now, I know interest rates go up and down, but we'll go at 6%. All right, how long are you guys going to be able to keep your hands off this money so we can let it grow in the account? 18? Everybody said 18. You wanted to go, what are you going to do, go buy a car? Okay. All right, so how much is in the account at age 18? This means your 18th birthday. All right, how's that sound? Let's take some guesses here, all my strong financial advisors. What do you think this will grow to by the time you're 18?
A lot of money.
Give me a number. How much?
$10,000.
$10,000. Anybody else?
7,500.
7,500.
1 million.
Somehow I think you're off on that. Maybe if you gave me 5,000 every year, that might do it. That would be called an annuity. Remember, Aaron? That would be an annuity.
Yeah.
All right, so our formula is future amount equals P times 1 plus R over N to the NT. Don't forget to memorize this. Memorize, okay? All right, plug and chug. What's my P? 5,000. What's my R? 0.06. What is my N? 12. Where did that 12 come from?
Compounded
Monthly. How many times interest is tacked on in a year? Okay. And N is 12 and T is 18 because you're going to leave it there for 18 years. So we have 5,000. All right, if you do 0.06 divided by 12 on your calculator, that's 0.005, I would bet. Okay, and 12 times 18, 216. All right, we're about ready for the grand finale here. So remember, you take care of exponents before multiplication. So we got 1.005 raised to the 216 power. So we have 5,000 times about 2.936766597. You just keep enough decimals so you can round it to dollars and cents. Times 5,000. Ooh, I did it too many times. Somebody double check me. I got 14,683.83 about. Does that sound good?
Yeah, 83.
Okay. All right. So they gave you $5,000. Put it in one of those college funds for you where you can't touch it till you're 18, and it grows maybe hopefully interest free for you. And it grows to $14,683.83. So the amount of interest you earned was, what, $9,683.83? All right, now if you could just talk your uncle to put it in $5,000 every year for you and not just one time, life would be great. All right, everybody good? All right, let's...
$5,000 every year and plug it into this one?
His question was, if the uncle was going to give you $5,000 every year, could you plug it in this formula? No, this is a one-time deal. It's called an annuity. you could technically, it's easy to set up a spreadsheet to do that, and there's also formulas for annuities. Math 105 is a fun class to take, guys. Take Math 105, and you do these kind of annuity problems. There's not a below here. It is a different course. Math 105, lots of people take Math 105. It's not below. It's a great course. Everybody loves it. You know who wrote the book. Okay. All right. So it sounds like to me you guys are wanting a certain amount of money. So let's do it this way. You need how much do you need? You don't really need that.
$50,000.
All right, you need $50,000.
No, twice that much.
All right, how much do you have now?
$0.
Well, that's going to be hard to grow if you start out with nothing. All
$10.
right, let's say you have, we'll all get together here.
50.
We'll say you have, let's do something kind of reasonable, $1,000. You have $1,000 now. You can invest at, by the way, do you know what a financial planner would say that if you were a good investor, you should average over a long period of time per year? Uh-huh. 20? What kind of financial advisor you got?
It's not 20. No, you're right. Because it should be 20% out of each paycheck you should be saving.
Right, but how much should your money grow year after year if you are a wise investor?
5%.
No, they will say 9% minimum over the long run. So we're going to say you're good. 9%. You can invest at 9%. We'll just do this annually. How long must you wait for your vacation? That's why you wanted $50,000, right? Oh, you wanted a car. $50,000 car? Okay. All right, you need $50,000, I'm going to say, for a vacation. Might need it for the nursing home. It might take so long. You have $1,000 now. You can invest it at 9% compounded annually. How long must you wait for your vacation? Does that sound good? What am I going to be looking for? Time, exactly. All right, A equals P times 1 plus R over N to the NT. Okay, what's my A? 50,000. P is 1,000. R is 0.09. N is 1 raised to the T. Okay, so our job is to solve for T. What's my first step, everybody? What's this equation called? Is a what kind of equation? Exponential or log?
Exponential.
Exponential equation. So we know how to solve those. So what's my first step? Divide both sides by 1,000. So if I divide that by 1,000, that probably is 50 equals 1.09 raised to the T. Everybody good with me? All right, how do I solve for T? Okay, you could put it in log form, or I really like just taking the natural log of both sides, so I don't have to use change of base formula. Is that okay? Okay, so let's take the natural log of both sides. If I take the natural log of both sides, where does this T right here go? In front. T natural log 1.09 equals natural log of 50. So T then is going to be equal to natural log of 50 divided by natural log of 1.09. And let's just punch away on our calculator and see how long it's going to be before you can take your vacation. You might decide you just want to go down to a swimming pool somewhere. Okay, natural log of 50 divided by a natural log of 1.09. This is the grand finale. How many years you got to wait? Whoa! It's going to take approximately 45.39 years. That's more than a third. So that's 45 years, and that's a third of the year would be about 4 months. So it's going to take about 45 years. Thing I would say is invest a little bit all along if you're trying to hurry up and get to your $50,000. But it would take about 45 years for this to grow. Now just think if you were doing it at the 3% your bank accounts are now earning. You would be dead. All right, you leave it for your children to fight over the money. All right, everybody good? All right, now following this, A equals P times 1 plus R over N to the NT. If you were going to let N be approximately 365, N be approximately 365, and I'm watching the time, so I'm just going to tell you what's going to happen here. As N approaches 365, this expression in here will start to approach E, and I was going to derive that for you, and it's derived for you in your book. But as you start compounding more and more often, and it's very close to daily, this expression in here starts to approach E, and you have what is called compounded continuously. Compounded continuously. This is a great little proof, but I'm watching my time. All right, this is a very easy formula to remember because it reminds you of some shampoo. Do y'all see the name brand of any shampoo right here? Pert shampoo. Pert Plus. All right. PE to the RT. All right. So if you have something compounded continuously, this little formula works really nicely. All right. And if we had time, we would do a compounded daily for maybe a year and a compounded continuously for a year, and I'd show you they were about the same. And your book is really good at showing you all this stuff. But I'm going to jump to the problem. All right. Find the future amount of $500 invested at 6% compounded, and the words are continuously. Compounded continuously. All right, if it didn't say compounded continuously, but compounded monthly, quarterly, daily, you had to use the other formula. But compounded continuously, we'll use shampoo. All right, A equals, P is your 500. E, the R is the rate you see named in the problem, 0.06. And what did I leave out of the words here? How long I was going to let it grow, right? Find the future amount of $500 invested at 6% compounded continuously for 8 years. And so we'll multiply that times 8. Okay? All right, remember you have to do your multiplication first in your exponents. That's E, 0.06 times 8 is 0.48. And then you just plug and chug on your calculator. So you have E raised to the 0.48, and then multiply that times 500. And it gives you $808.04, approximately 04 cents. Okay, compounded continuously. There are no banks that I'm aware of that does compounded continuously. If you did a compounded daily with N equal to 365 and your time equal to 8, you're going to come out pretty close to this. So this is a nice little tool for making some quick approximations to things. Okay? All right, let's change the problem. At what rate compounded continuously will let's do your problem. 50,000, will 1,000 grow to 50,000? And you guys didn't want to wait 45 years, so you want to wait just 10? To 50,000 in 10 years. A very high rate is going to be the answer. At what rate of interest compounded continuously will $1,000 grow to 50,000 in 10 years? What's your formula?
PRT.
Okay, it is your shampoo problem. A is 50,000. P is 1,000. You're looking for R, and T is 10. Okay, this is an exponential equation. What are you going to do? First step, divide by 1,000, and you get 50 equals e to the 10r. What's your next step? Natural log both sides. The natural log of e to the 10r is 10r. So r then, which is going to be our interest rate, is natural log of 50 divided by 10. Okay, let's see what that is. Anybody want to guess before we punch? Going to have to be a very high, impossible. This would be a long shot situation, right? You can't go from $1,000 to 50,000 in 10 years without some funny money going on there. Okay, natural log of 50 divided by 10, and that gives me that R is 0.39120. How do you change that to a percent? Move it over 2 decimal places. 39.12%, and that's beyond the legal limits in North Carolina.
What's the legal?
The last I checked, the legal limits that could be charged on some of these side streets was, I think, 30%, but then they can always add in these fees and handling and all these little other things that jack it up. But you'd have to be earning about 39.12% compounded continuously to get that money to grow to that in 10 years. Okay? That doesn't always happen. That doesn't happen very often at all. All right, everybody good? Okay, so these are applications of your solving your exponential and your log equations, taking a log of both sides or going from there. All right, let me mention 4.8, and then we'll pick that up next time. So you can go ahead and be working on it. Don't forget your cumulative review. I just want to point out on that page 473 in number 1, all of a sudden they're going to change the symbols for you. They're just changing symbols. But I claim if you can handle shampoo, you can handle the exponential growth curve. Just because they call it a sub 0, there's no reason why you can't call it a P and an E to a RT instead of a KT. The K and the A's are just representing symbols. So when we do exponential growth curves, your compound interest money that you're earning on your account is growing exponentially. So when we're talking about a population growth, we can just use shampoo as well as we can use A, E to the RT. So I know that sometimes students go, oh gosh, more formulas to memorize. Really, there are no more formulas to memorize. It's just different letters, and I don't know if I use always the P's or the A's or whatever. And so section 4.8 is going to be very easy for you because you already know how to handle compounded continuously, and that's what it is. Okay? All right, we will start there next time, do cumulative review, and hopefully start some trig.